All right. The assignment that covers evaporation and infiltration, which we're going to start talking about infiltration today, that's due on Thursday at noon. And then that's when I'll have the solution program to release, so that then you've got 24 hours to look over the solution for homework 5 before we have the midterm exam the following day. And I'll give you more details next week about the midterm, but one thing I wanted to put on your radar now is that you'll need to have a computer for that exam. And I'm still thinking through what I'm going to include for that, but it's going to have at least one computer-based question, whether it be HY8, StormCAD, or like a pond sizing problem where you'd need to have Excel. So you ought to have all 3 of those ready to go for the test. Now today we're going to start talking about infiltration, which is a really important phenomenon because it determines how much of the rainfall that hits the ground surface is turning into rainfall excess, which is what contributes to runoff. So it's important that we both understand the fundamentals of why infiltration occurs and what are the factors that determine the rate of infiltration, but then also we'll look at some methods that have been developed to try and calculate and quantify the rate of infiltration and the infiltration depths. Before we get into that, we just have to very briefly finish talking about evaporation. And one of the ways that we can measure the effect of evaporation is by setting pans of water out and measuring how much of the water evaporates in a certain known period of time. And then we can, over the course of time, develop relationships between how much water evaporates out of the pan and then how much water would evaporate from other things that we're interested in, like from certain crops. And so you could set a pan out in a field of grass, for example, and then obviously how much the water goes down is going to be reflected both by the precipitation that occurs during a certain period and then also the combined effects of the solar radiation, which drives the latent heat of vaporization, and then also the wind and the relative humidity effects, and whether there's a gradient between the saturated vapor pressure and the vapor pressure of the moisture in the air at a given humidity level. So these pans take both of those into effect. And ET, this term here, sometimes we think of it as evaporation, and sometimes you'll hear the phrase evapotranspiration, because transpiration is the process by which plants exhale moisture during their cellular activity. And so some texts draw the distinction between evaporation, which is more of the water directly coming from the surface. So maybe if there was a droplet of water on the top of a leaf, but then that droplet of water evaporates, that would be evaporation. But then evapotranspiration would be when it comes out of the plant material itself. And so there are these tables that exist that relate the evaporation that you'd see from a pan of water to how much evaporation you could expect from a short green crop, for example. And how much evaporation is going to occur from the crop relative to the pan varies on several things, like the amount of wind, how much of the crop the pan is surrounded by, because if the pan is surrounded by, on all sides, by the crop, then it may be that the crop's evapotranspiration is saturating the air, so that then by the time it gets to the pan, there isn't going to be as much evaporation as there otherwise would be in an upstream location that didn't have that moist air, where the plants had already evapotranspirated. So you can see that there's a variety of different factors that are accounted for, including the humidity, and then these pan coefficients are a decimal that then you would multiply the observed pan evaporation, E sub p, by the pan coefficient, and then that would tell you how much evapotranspiration happened out of the crop, and then that would be the amount of moisture that you'd have to replenish through irrigation or, hoping for rain in order to ensure that there's an equilibrium between the inflow of the water to the crop and the outflow through evaporation and transpiration. So, there's numerical models that will help to estimate evaporation. We have direct physical measurements with these pans, and it's an important process that we have to be able to quantify. All right, we're going to spend a moment watching a really valuable YouTube video, and I was looking at the comments yesterday and someone described it as an entire semester's worth of information distilled down to in just a few minutes. Now, if the entire course was about subsurface flow, that could be true, but for us, subsurface hydrology is just a small part of our overall course. But this is a really important video. There's like behavior that you're going to see in this video, just how the water moves through soil, that I've never seen it represented kind of as clearly and as well in other sense. So let's watch this. Let me turn on the sound, pause the recording. The remaining experiments that they do maybe repeat some of the same information, but the takeaway messages that I hope that you learn from this is, number one, just a visualization of how the water penetrates through soil, and talking about some of the forces and factors that determines how quickly it moves. So we've talked about things like the hydraulic conductivity of the clay layer, and how water moves through clay. It penetrates quickly, meaning it can get into the clay layer. This initial wetting front enters easily, but then it moves slowly through the clay. And then in contrast to the sand, the water has a difficult time entering the sand and won't do so until all of the voids in the loam are saturated and the suction pressure is low in the loam, and then it can finally begin entering the sand, which has the lower suction pressure. But then once the water gets into the sand, it moves very easily because sand has a high hydraulic conductivity. It can convey water very easily. So I learn something new every semester I watch that video. Let me bring the lights up. Okay. Now, how many of you have taken soil mechanics, geotechnical engineering before this semester? Has everybody taken it? And some of you are taking it this semester, right? Okay. Well, I'm not sure if you're yet at the part where you've talked about Darcy's law, but Darcy's law is a way of modeling how water can move through soil. And so imagine that this is a pipe that is packed with soil. And then connected to that pipe is a tube that's connected to an upper tank where the water elevation is high, and a lower tank where the water elevation is low. And so H1 means, H means the total head, but in a tank of water that's not moving, it's just the elevation that's represented within that head. Because it's not velocity, and it's open to the atmosphere, so it's not any additional pressure. So we could just think about the elevation of the water in this tank, but what Darcy's law does is it predicts the flow rate through this pipe that's packed with soil. So if it's packed with soil and we saturate the soil, so it's all become fully wet, the voids are full, then the flow rate Q, and of course you know that units of flow rate would be volume per time, is equal to A, the cross-sectional area of that pipe. So A would be like the front-facing area of that pipe. And then the driving force is the difference in elevation between the upstream and the downstream tank divided by L, which is the length of this pipe that's packed with soil. So if we multiply the area by that gradient. The gradient is the driving force that's pushing. The whole reason why water's flowing through this pipe packed with soil is because of the elevation difference between the upstream and the downstream tank. So there's a proportionality factor, K. The hydraulic conductivity, which has units of length per time. Oftentimes you'd see it expressed in centimeters per day, but you could also express it in terms of meters per second. It's just going to be really, really small, particularly for something like clay. This proportionality factor describes how easily water can flow through a soil that's already saturated. So that's one of the things that we have to kind of be familiar with to predict how quickly water moves through soil, is this idea that there is a parameter, K, the hydraulic conductivity, that describes how readily water moves through soil. And like I mentioned before, clay has a really low hydraulic conductivity. In fact, clay is so good at avoiding the transmission of water, I guess you could say it's bad at conveying water. They use compacted clay under landfills as a protective layer. Like when they bury garbage, they'll have sometimes a couple of feet of compacted clay at the bottom of the landfill, and then they'll cover a layer of plastic, and then they'll start putting the garbage on top of that. But the reason why they have that compacted clay is they don't want any contaminated water from the garbage to get into like the groundwater, into underground aquifers. And so clay is used to prevent the movement of water out of buried landfills. So that's clay. At the other end of the spectrum, things like sand and gravel have a very high hydraulic conductivity. So when it rains, the water begins to penetrate downward through the soil. And let's talk about this figure for a little bit. Of course, it's raining at the surface, and this horizontal line represents the ground surface, and then the depth is increasing the further downward we get. There's a wetting front that's getting progressively drier and drier. And so this line just represents how moist it was before the rain started. So what we're looking at is increasing moisture content as you go to the right, because at the top of this figure where it's raining, we assume that the water is entering the soil, and there's going to be a certain zone in which all of the voids in the soil are fully saturated. And then the further down you get, it's less and less water content. And so here the moisture content, the furthest it can get would be saturation. And then there's this progressively declining amount of water. And so you can see it's divided up into the wetting zone, which is the dry soil that's just getting exposed to additional moisture, the transmission zone where it's in between saturation and wetting, and then the saturation zone is the point at which all of the voids are full. So during a storm, the water gets downward through the soil, and of course this is just thinking maybe in one dimension, because what we know from that previous video is it's also moving outward. But let's assume that it's raining over a large area, and so it makes sense for us to think one-dimensionally, because if we have a certain column of soil that we're looking at and it's raining in a wide area, then any particular element of soil that we're looking at, the water's just going to be going downward. It won't be going sideways, because the soil that's to the side of it is also receiving flow. That video we watched, water was just coming to one central location. There wouldn't be the same sideways movement if they were dropping water evenly across the entire thing. This is difficult for us to model, and so there is an approach called the Green-Ampt model that simplifies this into saying, let's assume that we have continuous ponding at the surface, and then there's fully saturated soil voids, and then at some depth it goes to the initial moisture content. And so rather than having this transition zone, we're only going to have a saturation zone and the wetting zone, which is the border between saturation and the initial moisture content. And so here, they're using theta to talk about how much moisture is in the water. And so theta sub I, how much moisture is in the soil. Theta sub I is the initial water content, and then delta theta is the difference between the initial moisture content and when it's fully saturated. Porosity is a term that describes in a certain volume of soil how much of it is empty space. And so if you were going to take a cubic meter of soil, there's going to be grains in there, and this is maybe exaggerating the size of things, but let's just say that you look at some volume of soil and there's solid particles in there, but then there's also empty space. And porosity is the ratio of empty space to the overall volume. And that's what this is saying, is that the maximum amount of water content that you can have is equal to the porosity. When all of the voids are full of moisture, then that's maximum saturation. So this Green-Ampt simplification is just a way for us to calculate how quickly the water is moving downward. And it starts with this Darcy's law. The thing we looked at before that was describing the volumetric flow of water through a packed column, and the driving force being the gradient of head divided by the length. And so if we, instead of thinking about flow rate in volumetric terms, so if we take out the A, and we just want to know what's the speed of water moving through the soil, so the velocity, rather than Q equals VA, we just want to know the velocity. So the infiltration rate, how quickly the water is moving down through the soil, is, you can see, a function of the hydraulic conductivity, the depth of water that's above the soil, and so H naught is how deeply pooled the water is, and that's going to, the deeper the water puddle is at the surface, there's going to be more force driving it down through the soil. There's going to be an active pressure pushing it. And then this other term is taking into account the wetting front soil suction head. And so that's something we can look up for different types of soil, how much suction pressure they have that's drawing the water downward. Now, there's a simplification that says, if we just assume that there's continuous ponding, but it's just enough so that there's always excess moisture at the surface, and it's not getting like a really deep puddle, then we can simplify this just to say it's K, the hydraulic conductivity, and then the wetting front soil suction head, and then whatever length it's penetrated down through over time. And so there's a declining rate of infiltration, where at the beginning, when it just barely starts raining, the infiltration rate's going to be very high because L is small. So think about what's happening to the rate of infiltration just from the standpoint of the algebraic arrangement of this formula. When L is small, the rate will be large because we don't have very much in the denominator. But over time, as the water penetrates more deeply, L is getting larger, and that's going to have the infiltration rate decrease. And so from the conceptual basis, the reason why that's doing that is just more of the soil has had the suction head satisfied by filling the soil voids with water, and so there's less of a driving force. The longer L becomes, then there's not as much gap between how much water could be in the soil and how much water is in the soil, and so there's less of a driving force, and the rate decreases. So this is lowercase f is infiltration rate in terms of length per time. That's lowercase f. Capital F is cumulative infiltration, and so it's an amount. It's not a rate. And so if we wanted to monitor how much water was in the soil over time, if we took snapshots of what the wetting front looks like, you can see here at the beginning of the storm, at time 1, there would be more moisture at the surface than the further down you get, you're just getting to this initial water content. But the longer you have the storm, a certain depth of it is fully saturated and it penetrates to a certain depth, but then we have this decline of water content. So if we integrate the infiltration rate over time, then we can find the cumulative infiltration depth. And this is a really important figure. We've got a rainfall hydrograph, which you've seen before, these hydrographs. So here on the vertical axis, we're representing several things simultaneously. The rainfall rate, and that would be maybe inches per hour. And so remember, this could potentially be a storm that was like 2 inches per hour for 1 hour, and then 1.5 inches per hour for an hour. And this looks like maybe 1.7 inches. It's just, we are measuring the rainfall intensity over a certain period and finding out what's the average intensity during that period. So this curve, lowercase f, is the infiltration rate. And so anything under that curve is going to be the moisture that's getting into the soil. And anything above that curve you can see is labeled as rainfall excess. And so that is the moisture that it's rainfall that doesn't infiltrate, so therefore it runs off. So that's what's going to be contributing to flooding, is the rainfall excess. And so we could use similar units, you know, if we had inches per hour for the infiltration rate and inches per hour for the rainfall rate, then we could calculate the area above the infiltration rate curve but below the rainfall hydrograph curve, and we could know from that the volume of water that has to be accommodated. And so then capital F, you can see that is the cumulative infiltration amount. So just looking at it as a column of soil, we want to be able to predict how quickly the water is getting down through that soil to what depth, L. And the equations we have to calculate that start off by knowing that the infiltration amount is going to be whatever depth the water has penetrated to. And remember, full saturation is porosity, and then this is the initial water content. And so the difference between the two is what fraction of the voids in the soil had empty space. And so this is unitless. Porosity and water content are unitless. They're just going to be some decimal less than 1. And so porosity minus the initial water content is how many of the voids had available space, and then L, the penetrating depth, is a physical measurement of how far the water's gone. And so then the depth of water, you know, how many inches of water has infiltrated down, if the difference between porosity and initial water content, if porosity is 0.5 and the initial water content is 0.25, then that would mean for every inch of rainfall that penetrates, it would actually have a physical length of 4 inches. So it's going to penetrate further. You know, if you have 1 inch of rainfall that goes into the soil, L won't be 1 inch. It's going to be more than that because a lot of the voids already had moisture in it, and then a lot of the volume is solid soil rather than void. So we want to be able to predict over time how deeply the water has penetrated. So what is the length of the wetting front at a certain time t? And this is the equation that we solve to do that, the Green-Ampt equation. And remember, as complicated as this looks, we've already made a pretty big simplification to use it. We simplified what we know to be kind of a curvilinear wetting front into a binary wetting front, where we're saying it's either fully saturated or initial water content. So the Green-Ampt method isn't the simplest approach, but it does make things considerably easier than if we were trying to model that gradual increase in moisture content over time. Now what makes it tricky, if you've looked at it for a second here, is what we're trying to predict is the infiltration depth. So F is the unknown, and it's both on the left-hand side of the equation and the right-hand side of the equation. So that is an implicit equation. And if you remember, the Colebrook equation is similar, where the Colebrook equation, which we learn about in hydraulic engineering, is that one, it's an approach for calculating the friction factor F in a pipe, and F is on the left-hand side and the right-hand side of the equation. So the way that we have to solve this Green-Ampt equation is by starting with a guess of F and seeing if the right-hand side of the equation and the left-hand side of the equation equal each other. And once we know the cumulative infiltration depth, we can get the rate from that. Remember, lowercase f is the rate, meaning length per time. You know, during a certain period, how quickly was the water penetrating down into the soil? And so if you look at some of the variables that are in there, we need to know for a certain soil what's the hydraulic conductivity. We have to know the suction head. We have to know how much increase in moisture there was. And so ordinarily that increase in moisture content is going to be the effective saturation multiplied by the effective porosity. So we have to know how many of the voids in a soil are capable of carrying water, because some voids, like in lava rock, may not actually be connected. They're just a void that's surrounded on all sides by a solid, and so it can't actually carry water. But the interconnected voids are the ones that can carry water, and so this delta theta is how much water can be accepted by the soil. And so once we know the infiltration depth, we can estimate the infiltration rate from that. So we're going to look at an example. We're running out of time for today, so we won't get started on it today, but I've put a template in Blackboard that we're going to use at the start of class on Monday next week to do some calculations where we're going to have a soil where it tells us the hydraulic conductivity, the suction head, the soil characteristics like this, delta theta will be defined, and then we're going to want to know after 6 minutes and after 12 minutes, how much water got down into the soil, assuming that it's been raining the whole time. So, we'll know it's raining a certain amount and how much of that rain got into the soil. So we'll start with these givens, and we'll start by putting in all the soil characteristics into this Green-Ampt equation, and then we're going to start with a guess of the F value. And luckily, this isn't one of those where it takes too much effort to get the right-hand side and the left-hand side to equal. We'll just be able to use goal seek or solver, and it will converge pretty readily for us, and then that will tell us at a certain time how much water has penetrated down into the soil. And then once we know that infiltration depth, we can determine the infiltration rate from it as well. All right, so it's 12:48. That's all we've got for today. We're going to start next time by looking at some of these soil properties, and then we'll get into the example. Just remember that the assignment that you're working on right now includes both evaporation and infiltration stuff. And so we've covered all of the things that we're going to talk about for evaporation. This evaporation assignment, it's more than just plug and chug into equations I've shown you before. It requires a little bit of application. The solar radiation data that I've put on Blackboard, you're going to have to estimate the evaporation each hour of the day, because you're going to have a measure of the intensity of the sun, and so you're going to have like a measurement of the temperature of the water. So that combined approach that we did, remember this example of the combined approach, you're going to apply it for every hour of the day that it's sunny in that homework assignment. So it's kind of, I think it can be all set up on a spreadsheet pretty easily, but I wouldn't want you to leave that to the last minute. So I'd suggest that you get started on the evaporation stuff, and then if you've got questions, that gives you time to ask me. All right, that's it for today. I'll see you on Monday.